Okay, hello everyone. Welcome to our first seminar of 2026. We are really happy to have our own alumni, Saarik Kalia, to come back to us. Saarik now is a postdoc at Barcelona. After enjoying just merely 2 months of the sunshine and the beach, he decided he needs Minnesota so much. So come back to us and share with us his work. For those people who don't know him, Saarik graduated from Stanford and did his first postdoc with us for the past 3 years and moved to Barcelona in October. But he has many different new work already coming out. This is, I believe, his single author paper. We were really excited to hear his work. Okay.
Yeah, thanks so much for the nice introduction, John. Glad to be back. Glad to see everyone's faces again. Also very glad to have left warm, sunny Barcelona for this. I've been having a good time in Minnesota so far, and then I'm excited to tell you guys today about a recent paper I put out back in October. This is actually stuff that I did a lot of this back when I was here, but only put it out somewhat recently. This is a recent idea I had on a generic mechanism to generate blue-tilted isocurvature. So today's talk is going to be about cosmological fluctuations, so particular isocurvature fluctuations. So I wanted to start off by just reviewing what we know about cosmological fluctuations. So we know that on large scales, the universe is relatively homogeneous, right? So you'll see maps like this of the CMB, which are telling you that some parts of the sky are a little hotter and some are a little colder. But of course, the sky on the whole is fairly uniform, and these fluctuations are fairly tiny compared to the average temperature of the sky. So any good model of the universe should be able to reproduce these small fluctuations. And in particular, we have one very good model for this. This is called inflation. Basically, some early period of accelerated expansion can easily reproduce this. Now, there's another thing we know about fluctuations on large scales, which is that they're so-called adiabatic. And basically what that means is that they're correlated between different components, right? So if this spot here has a little bit more radiation, then it also has a little bit more dark matter and a little bit more baryons. Whereas if this spot has less photons, it also has less dark matter, less baryons, etc. So again, any good model of the universe should also be able to explain this as well. Now, there's a fairly simple reason why you might believe that this is the case, or a simple way to explain why this is the case, which is just if everything came from one component. So say early on during inflation, we just had one component called the inflaton. And then all the photons, baryons, dark matter we see all come from that one component. Then of course they all inherit the fluctuations of this inflaton. So it's then not so surprising that all of their fluctuations are correlated. Right, so this is a scenario which would lead to adiabatic fluctuations. By contrast, if we had some other component sitting around during inflation, which has its own fluctuations, if that component only gives its fluctuations to some subcomponents, but not others, say dark matter, but not other things, then we wouldn't see correlated fluctuations. So this is something we call isocurvature fluctuations. And basically, again, we don't see this on large scales, so any good model of the universe should not produce these types of isocurvature fluctuations on large scales. This is precisely the type of scenario that I'm going to be talking about today. Now, everything I've said so far really only applies to large scales. When you think about much smaller scales, basically anything's fair game. We know fairly little about what happens on smaller scales. So on smaller scales, you can have much larger fluctuations. You could have isocurvature fluctuations. And indeed, these are sort of interesting possibilities to consider because they can have interesting signatures like gravitational waves or non-Gaussianities. These are things that could be created by small-scale fluctuations. So enhanced fluctuations are kind of an interesting idea to think about. Now, today I'm specifically going to be talking about the fluctuations of scalar fields. So as we'll see today, there's a sort of generic statement that if you have a scalar field sitting around during inflation, then it's going to develop fluctuations of its own. And in particular, because these are fluctuations coming from a component which is not the inflaton, then as we saw, these will be isocurvature fluctuations. Of course, scalar fields are kind of ubiquitous in a lot of models of new physics. So this is all just to say that isocurvature fluctuations are not just something you could think about, but really something you should think about whenever you write down any new models. So that's what we're going to be studying a little bit more today. More specifically, the claim that I made here about scalar fields getting fluctuations, what I really should have said is that if the field is very light, so if the mass is much smaller than the Hubble scale during inflation, then that typically means that it gets isocurvature at all scales, both large and small. And as we saw, isocurvature fluctuations on large scales are constrained by CMB observations, and therefore this scenario is somewhat constrained. On the flip side, if the field is very heavy, if it's much heavier than the Hubble during inflation, then typically you would get no fluctuations at all. So typically you're in a scenario where you're either constrained or you're not going to get any interesting signatures to look for. However, if you're kind of in this sweet spot where the mass is roughly comparable to the Hubble scale during inflation, then you get this nice feature which is called a blue tilted spectrum, meaning you don't have many fluctuations on large scales, but on small scales you have enhanced fluctuations. So this can be consistent with observations while also having interesting signatures you could look for. So this is a nice possibility, although it sort of requires this somewhat tuned coincidence of scales. You need the mass of the field you're thinking about to be similar to whatever the Hubble scale is during inflation. And in particular, if you're like me, you like thinking about ultralight dark matter, then this may be somewhat problematic. Of course, there are various games you can play to try to get around this condition. People have done various types of model building. You can do things like give the field an effective mass during inflation from some non-normal coupling to gravity or some coupling to the inflaton. So it has a mass during inflation, but then you take it away later. So you get some light field, but it still has this blue tilted spectrum. So people have thought about these types of scenarios.
Does your classification depend on the coupling, the type of coupling? Right? Are you assuming simple, just multi-scalar couplings with no derivatives? But with derivatives, it will be different.
This doesn't so much have to do with the
light one does depend on the other one, heavy and blue tilted.
Again, that's not so much, doesn't so much depend on the couplings. I mean, I guess there's a somewhat inherent assumption here that I'm assuming the couplings are weak enough, so you're like treating it as mostly a free massive field. Yeah, but it doesn't rely on any couplings.
You're going to show us the Lagrangian here.
Yeah, like I'll explain where exactly these come from in a little bit. This is more just a heuristic overview.
And you're thinking that this field is also dark matter. It's not just something that generates the fluctuation.
Yes, eventually I will want it to be dark matter, but also a lot of what I'm going to say also applies to just spectators. Yeah. Good. So there are two main takeaways of this talk. One is that getting this blue tilt is actually not as hard as it might seem. You don't necessarily have to do as much complicated model building as you might think. But actually, rather generically, we will see that inflationary dynamics can give you this blue tilt. Basically, this requires two conditions. One is that inflation doesn't last too long. We'll see why that is important in a moment. And then also the scalar has to have some non-trivial potential. Importantly, we'll see that actually the exact shape of the potential is not important. This can work for a wide variety of potentials and a wide variety of parameter choices for those potentials. So in that sense, this is a fairly generic mechanism. It's really the inflationary dynamics that are going to give us the effect we want, this blue tilt.
Now, you can say, what is the trivial potential?
Sorry, not just a mass. Yeah, trivial potential is just a mass. Sorry, I maybe should have said that. So some like self-interacting potential. Good. The second point is that this mechanism is actually also going to function as a valid production mechanism for dark matter. If this scalar spectator is indeed long-lived, then I can actually get it to be dark matter. Basically, we'll see that it'll be left over at the end of the day with some relic abundance, and by enforcing that relic abundance is the correct relic abundance to be dark matter, that will give me some relationship between the parameters of the potential. It'll allow me to draw some line in parameter space, which tells me that dark matter lives here, much like, you know, the misalignment line for axion dark matter, for instance. So at the end of the talk, I'll actually show you what that line looks like for quartic dark matter, and I'll show you where the well-motivated parameter space for that is. Good. So before I get into too many details, I just wanted to show you a schematic picture of what this mechanism looks like. So I'm going to be thinking about a scalar field, which is living in some non-trivial potential. here. So again, not just a quadratic potential. And I'm going to be thinking about its dynamics during inflation. So this potential, much like the inflaton, this field will also have some slow roll solution, which is valid when some slow roll condition is satisfied. I'll tell you in a second what that slow roll condition is. And so this potential is going to have some regions which satisfy this slow roll condition and some regions which don't, which I'll call fast roll. So I want to let me think about the scenario where my scalar field begins in a regime of the potential, some fast roll regime of the potential, and is rolling towards the slow roll regime. And let's see what happens during inflation. So what happens at first? As the name suggests, the field should begin fast rolling through the fast roll regime. And so it should very, very quickly come to the boundary of this regime, the boundary between the fast roll and slow roll regime. Once it gets there, then it enters the slow roll regime, and then again, as the name sort of suggests, it will be slow rolling from then on. What the upshot of all of this means is that the field is going to spend a majority of its time near the boundary of this slow roll regime. For most of inflation, the field is near the boundary of the slow roll regime, and therefore, for most of inflation, the slow roll condition is marginally satisfied. That's kind of the important point that just comes naturally from the dynamics. Okay, now what is this slow roll condition that I've been mentioning? We will see that the slow roll condition is that the second derivative of the potential should be less than Hubble squared. So the second derivative of the potential is basically like an effective mass. So what all of this is telling me is that the inflationary dynamics are naturally going to put me in a scenario where the effective mass is slightly less than Hubble. Slightly less, but not too much less. And recall, this is precisely the condition that I wanted in order to get a blue tilt. So all of this is telling me that the inflationary dynamics will naturally put me in a part of the potential, which will give me a blue tilt. And so it's a fairly generic result that I should expect. Okay, so this is the rough outline of my talk. I'll spend the first part of the talk discussing the dynamics during inflation. So I'll first talk about what happens to the condensate. I'll be thinking of a scenario where the spectator is mostly homogeneous, so it'll be a condensate with some small perturbations. So I'll first discuss what happens to the condensate. That'll basically be fleshing out that picture I just showed you. In particular, I will derive the slow roll solution for this scalar field, and I will show what the slow roll parameter that governs that solution is. Then I will discuss what happens to the perturbations. I'll show that the perturbation spectrum has some blue tilt to it, and in particular, that tilt will be controlled by the slow roll parameter that I derived in this first part. Then in the second part, I will talk about what happens after inflation, what happens during radiation domination. So we saw from the last slide that at the end of inflation, the scalar field is sitting somewhere on its potential, so it has some energy density to it. We can just track how that energy density evolves throughout radiation domination, and it'll be left with some relic density today. So by enforcing that relic density is equal to the dark matter density, then I can find what parameters give me the exact right amount of dark matter. And as I said before, this will enforce some relationship between the parameters of the potential, so I can draw some line in parameter space where I get the right amount of dark matter. Now, importantly, because the mechanism that I just showed you relied on an attractor solution, it's insensitive to the initial conditions of the scalar field, which means that ultimately this line I'm going to draw in parameter space is robust to initial conditions of the field. So in that sense, this line is going to be somewhat robust, which will make it a good experimental benchmark. And then finally, I'll discuss what happens to these perturbations as they go through radiation domination. And they basically will find that not too much happens. They get some order 1 factor, but it's not, the tilt itself will stay the same. Okay. Were there any questions on any of the intro? Okay. If not, then we can go ahead and get started. So let's start off by thinking about talking about the dynamics of the field during inflation. So I want to consider the scenario where the scalar is mostly homogeneous, so it's dominated by some condensate with some small spatial perturbations. This is a similar sort of assumption that you usually take for the inflaton. Even if you actually don't begin in such a scenario, even if you begin with a field which is somewhat inhomogeneous, inflation will kind of zoom you in on one part of the potential. So in that sense, this assumption is actually not too strong of an assumption.
So this is a spectator field that doesn't
Yes.
contribute to
Yes.
alone.
Yes, yes. So this field is going to be subdominant compared to the inflaton. Throughout this talk, I'm not going to actually deal with the inflaton. I guess I didn't write this anywhere, but I'm just going to, for inflation, I'm going to take exact de Sitter just to make things simple. Good. Yes, so I'm going to define this parameter alpha, which is v double prime over h squared. As we will see in a second, this will end up being our slow roll parameter. So this is going to be kind of an important parameter that we're going to deal with. So I want to track what the dynamics of this alpha look like. Good. So what's the equation of motion? So I can write down an equation of motion for this condensate. This is basically just a Klein-Gordon equation, but without the gradient terms because I took the zero mode. And there's some Hubble friction term coming from the expansion of the universe. Okay, so let's see how this behaves in different regimes. So let's suppose I start off with alpha very large. I start somewhere in the fast roll regime, what I've been calling. So then we can see that Hubble is relatively small, so I can neglect this term. In that case, then this just looks like the scalar field is oscillating in its potential, back and forth. Of course, this term is not completely negligible because it does cause the field to redshift. So the energy that this field will have some energy density to it. It will redshift with some equation of state. But the details of this equation are not important. The thing I just want to emphasize is that if I write things in terms of e-folds, then the energy density is going to change exponentially as a function of e-folds. Likewise, the condensate value and also this alpha. They will all go exponentially as a function of n. That's kind of the only important point I wanted to emphasize here is that things are going to decay exponentially when you're in this fast roll regime, when alpha is very large.
Are you guaranteed that when alpha is very large, that this is not contributing to the total energy density?
So yeah, you have to pick particular parts of parameter space to make sure that that's not the case. But yes, there will be available parameter space for
Because
this.
if you start from 5 and 0, that is
Yeah, I guess.
large deal 5.
So slight spoiler, but these are kind of the going to be the conditions that we're going to need.
The last one.
Yeah, so this is that the spectator is subdominant. This is what you're worried about. This is the condition that you start with alpha very large, beginning the fast roll regime. And you can convince yourself that there's parameter space where you can satisfy both these things. Because if you take n song very large.
Okay, right? Because the infloton density changes very little.
Sure, that is taking to be constant anyway, so that's okay. I'm just, well, what are the scales? What are you? I mean, normally you would think phi 0 is typically determined by the quantum fluctuations during inflation. So the phi 0 you would take to be something like h to the 4th divided by m effective squared.
Good. So your intuition may be coming from like a Fokker-Planck type distribution or something.
There no matter what, right? So it's hard to imagine it being smaller than that. I don't know if you want it smaller or bigger.
No, bigger
You don't want it to
than
be
that.
bigger
Yeah,
than that.
yeah.
But if it's bigger than that, then I wonder that you satisfy these constraints because
If the quartic coupling is very small, we can satisfy.
Yeah, so the initial values that I'm thinking about are going to be much further out than what the like Fokker-Planck distribution is. So the Fokker-Planck distribution is sort of the long time distribution that you reach after you let inflation evolve long time. So I'm really thinking about what happens before then. What happens before you get to that steady state distribution. So if I start with some prior where my field begins somewhere, can begin kind of anywhere on my potential. If I evolve it for long enough, I'll get to that Fokker-Planck distribution, which is centered around the middle. But in principle, if I just think about what's happening at the start, I don't evolve that long, then I can have my field arbitrarily far.
No, I mean, you can choose your initial condition to be bigger than that, so.
Yeah.
So, but then, so I'm just looking, so V, then I could, if I approximate V to be V double prime times phi squared,
Sure, yeah.
okay?
Uh-huh.
And then phi squared is bigger than h to the fourth, over,
Yeah. You can just take M Planck to be very large, and then this condition is completely independent of that condition.
maybe,
Right.
probably right.
Yeah. It's just you need to be sitting between h to the fourth and h squared M Planck squared, basically. Good. So we saw when alpha is large, then it decreases exponentially. When so I've been talking about this slow roll regime. So what exactly is what is this slow roll solution and when does it apply? So the slow roll solution is when I can neglect this first term here. When I neglect that first term, then I get a slow roll solution that looks like this. This is a similar equation to what you would see for the inflaton. And I can ask, when is that valid? It's valid when this second derivative is smaller than h phi dot. And you can convince yourself that if you plug this in here, you will precisely get the condition that this alpha is less than 1. So this is just confirming what I told you earlier that alpha is indeed the slow roll parameter. And so when you're in this slow roll regime, you can recast this equation in terms of alpha. I didn't bother to do that, but you can recast it. I didn't do it on the slides, I did it in the paper. You can recast it in terms of alpha, and you will find that alpha goes like 1 over n. So the upshot of this is that when alpha is much bigger than 1, then you decrease exponentially. When alpha is smaller than 1, then you go like 1 over n. Okay, so the upshot of all of this is that the dynamics are naturally driving you to a regime where alpha is going to be slightly less than 1. Because when it starts much bigger than 1, it rockets down to 1, and then it starts moving very slowly from there. So this is precisely showing you those dynamics. I'm taking 2 different potentials here of 2 different forms. And I see in both cases, if I start out with alpha very large, then alpha will begin to oscillate and decrease exponentially. And then later on, it'll go like 1 over n. These dashed lines here are basically showing some analytic prediction for that 1 over n. Generically, this coefficient will depend on the particular potential that I choose, the shape of the potential I choose. Generically, it'll be order 1. So this blue curve here is a quartic potential, and this is sort of a generic value you would get. But I include the orange curve here just to show that there are potentials for which this coefficient can be large. So you can see for this orange curve here, actually, for a lot of the time it spends, the alpha is actually pretty close to 1. So the upshot of all of this is that alpha is roughly like 1 over n, where n is the number of e-folds from the beginning of inflation to whatever point in time I'm at. As we'll see in a few slides, the tilt of the perturbation spectrum that I'm going to compute is going to be related to this alpha, and specifically it will be related to alpha at horizon posit. So if I'm interested in the tilt of my spectrum at CMB modes, then CMB modes exit the horizon around 60 e-folds before the end of inflation. So I'll be interested in the alpha at like minus 60. So you can see for this orange curve, that alpha is like almost 1. For the blue curve, it's still like order 0.1. Right, so this is kind of going to be the relevant alphas that will set the tilt of my perturbation spectrum. You can also see here why it was important that I assume that inflation was not too long, because if I take inflation to be very, very long, then this 1 over n will become very small. Okay. Yes, this is the slide I was showing before. These are just the necessary conditions for this mechanism to work. So I have to start in the fast roll regime. There should be some slow roll regime which exists in order for me to roll to. The kind of most critical condition of all these, I would say this one, that if I start in the fast roll regime, I roll towards the slow roll regime. This is a condition on the sign of the different derivatives of the potential. And in particular, this means that this mechanism It doesn't work for all potentials. It only works for certain shapes of potentials. So in particular, it doesn't work for a cosine potential. So it doesn't work for like an axion, but it does work for a quartic potential, as we'll see. And then yes, I also want the spectator to be subdominant the whole time. Okay.
Sorry,
Yeah.
even for axions, so long as I don't have too much kinetic energy to go across the different periods, wouldn't this condition be satisfied as well?
Not this one. So this like
This becomes sine
this
squared.
But this is negative sign and this is sine.
Oh,
Yeah,
So it's negative.
whenever you
Yeah.
differentiate the signs.
Yeah. So basically for a cosine potential, the top of the potential is the slow roll regime and the bottom is the fast roll. So you roll from slow to fast. You want the opposite. You want to roll from fast to slow.
I was thinking if we start from not the top, right, in this faster regime. This faster regime is the high gradient part. So it's still rolling towards the bottom. So I don't want to start at the hilltop. I can start at the
You want concave instead of convex.
Basically, yeah. Okay. Good. So I discussed the condensate. Now let me talk about what happens to the perturbations. How do the perturbations evolve, and where do I get this blue tilt from? So actually all the math in this part for the next few slides is all well-known stuff, but I figured it would be nice to spell it out for people who haven't seen it. Let me figure out first what happens to the perturbations if I just forget the existence of the potential entirely. So let me just take a massless free scalar field. This is similar to what I would get for the perturbations of the inflaton. So this is the equation of motion for these delta phi's. Again, this is basically just the Klein-Gordon equation, but now in Fourier space. I can make a change of variables to this, what I'm going to call f, which is basically just multiplying by the scale factor, and change my time coordinate to conformal time. And it turns out I get an equation which now looks like this. This describes how this f evolves, and I put it in this form because there's you can easily see some good, nice behavior from this. Early on, when the mode is sub-horizon, so the mode is still within the horizon, then I can neglect this 2 over tau squared term, and then you can see that this equation just looks like a harmonic oscillator, oscillating with some frequency k. Typically, you take some initial conditions, which are the Bunch-Davies initial conditions for this harmonic oscillator, but long story short, it behaves like a harmonic oscillator. Then at later times, once the mode has exited the horizon, then I can neglect this k squared term, and then I will find that f goes like 1 over tau, which means that delta phi will basically be constant. So again, this is the typical behavior you would expect for perturbations of the inflaton, that they will oscillate when they're inside the horizon, and then once they exit the horizon, they will be frozen. They will just be constant. Okay, all of this was without a potential and without a mass as well. What happens when I add a potential in? That'll just add some additional term, which actually looks kind of like this term. It also goes like 1 over tau squared. And that just changes the super horizon behavior. So rather than delta phi being constant, delta phi will now slightly decrease when it's outside the horizon. So long story short, the presence of this potential causes the perturbations to decay when they're outside the horizon. And the rate of that decay is determined by this alpha. Recall alpha is v double prime over h squared. That's why it's showing up here. So the rate at which these perturbations decay when they're outside the horizon is related to this alpha slow roll parameter I've been talking about. By the way, this works even for just a quadratic potential. So just a mass, you would get the same exact behavior here. Okay, so the upshot of the last couple slides was just to tell you that the presence of the potential, what that does is it causes the perturbations to decay when they're outside the horizon. So if I look at the spectrum, the power spectrum of my perturbations, then they will be suppressed by the integral of alpha for the entire duration of the time that my mode is outside the horizon. Right? That's what this integral is saying here. what all that means, importantly, is that the longer that a mode is outside the horizon, the more suppressed it gets. And in particular, that means longer wave-like modes, which exit the horizon earlier, so spend more time outside the horizon, they will get damped more. And shorter wave-like modes will get damped less. That's a blue tilt, right? So this is precisely where I'm getting my blue tilt from. You can see, and we'll see that the tilt of that spectrum is precisely related to this alpha parameter that we've calculated. Note that it's the alpha at horizon crossing. And so that's why I was pointing out earlier that the alphas around -60 are really the ones we care about. Okay, so if I take those two potentials that I showed you a while back and I compute the resulting perturbation spectrum from them, then I can get power spectra that look like this. This is the isocurvature power spectrum for those same two potentials from earlier. I'm comparing them to various different existing constraints. And you can see that in both cases I get some sort of tilt so that I can avoid the constraints at large scales, but still get potentially interesting signatures at small scales. Recall that the blue curve had smaller alpha, so this tilt here is somewhat modest, although it's not completely negligible because you do see that it increases over many orders of magnitude, but if you have a large alpha, then you can get an even larger tilt. This dashed line, I'll come back to what that means, but yeah.
Can you comment on the power dependence? Why closer to 2 give you, since that's probably optimal blue tilt.
Yes, yeah. So maybe I can just show.
You don't do jump if you plan to.
Well, this is a backup slide. So I had told you that I could take that slow roll equation and I could recast it in terms of alpha and solve the equation. So I would have gotten something that looked like this, where this kappa is defined in this way. And if you solve it, then you get, as I said, you get alpha goes like 1 over n. This kappa is what that coefficient is. So kappa small means that I get a big enhancement. So you can see when p is close to 2, then kappa small. So yes, in some sense, having something close to a quadratic potential will give me a sharper tilt.
Yes, but exactly quadratic is just mass term. So
yes,
that
yeah.
trivial potential, you don't have a tilt, right? So they're saying once I,
Mhm.
2 have no jump and slightly different than 2, I have big blue tilt.
Yeah, so the trade-off comes in basically how long it takes me to actually get to this steady state. So I've been saying that you decrease exponentially and therefore you almost immediately get to the slow roll. But in fact, this coefficient here also depends on the tilt of the potential. So as you take p to be closer and closer to 2, you will get this coefficient out here to be larger, but you're also going to take a lot longer to reach the slow roll regime. So in that sense, there's a bit of a trade-off there. Yeah. Good. Any other questions on any of the inflation part?
Can
Okay.
you tell us a bit about the observational perspectives? You do the constraints, right? So, but what are the probes at the blue part, large K? What are the future probes?
Yeah, so this is actually a good question, because I think this space is not super well explored, especially at small scales. It's fairly difficult to probe any kind of structure. And it's difficult to probe the primordial spectrum on small scales because at small scales things get jumbled up by galactic dynamics. So it's definitely typically easier to probe things on large scales. I don't really know if there are any good like up and coming probes. I actually did talk to I got this CMB curve from it was a paper with Nico and Pager and some other people, and I actually asked them some questions about it, and I think that they said that this Lyman alpha curve here I took that from a different paper, but they said that there are people who are working on doing this analysis more precisely. And so if you do this analysis a little more precisely, you can maybe strengthen these constraints. But yeah, I don't know too much about the state of the art of that. But if other people know more about that, I would be interested to hear more about it. Okay. Good. So now I've discussed the
But the
dynamics.
idea that this field seeds the dark matter.
Yes, so up until now, this has just been a spectator field. So it could be the dark matter, it could be some other field. It doesn't have to be the dark matter. From now on, I'm going to make it the dark matter.
No, but even observational prospects, suppose this phi
Oh.
decays to everything at the same time.
Yes.
Then
Sorry, in this plot, yes, you're right. Actually, I did assume that it's the dark matter in this plot. Yeah. But in order to like this mechanism in general can work for a spectator, but in order to translate that into any observations today, what happens to it? Yes, yeah, exactly. So that is true. Good. Yeah. So now I want to think about what happens after inflation. So as Maxime alluded to, I want to think about the case where this is going to be a long-lived. The spectator is long-lived and maybe can actually be the dark matter today. So basically, I'm going to track its relic abundance, how it evolves over time, and compute what parameters give me the correct dark matter.
Does anyone remember there is also the talks about compensated as a curvature fluctuation? Say you have a strain on matter power spectrum, well, it fluctuates, right? And but then your baryons and dark matter fluctuate opposite to each other, but then overall the fluctuations are their body. This is scale called compensating. Where people discuss.
Well, I think
your field seeds both dark matter and
so I think typically isocurvature is defined in such a way that the total. So if you only had two components, if you only had like radiation and matter, then isocurvature is typically defined in a way where the total is conserved. It's like more radiation, less matter, so that the total stays the same. I guess what you're thinking about is sort of I have three fields. So like radiation is staying the same, matter is going up, and like dark matter is going up, baryons are going down, or something like that. Yeah, so I suppose you could have some scenarios like that. Yeah.
If people were speculating this might happen during the PV different outcomes.
Oh, okay.
But baryon of underfluctuation. Suppress the thing.
Okay. All right. I'm not super familiar with those. Okay, so we saw that our scalar field ended inflation with some energy density entirely in the condensate because it's sitting somewhere up on its potential. And so that means it has some energy density, and I can track that through radiation domination until today, and I can find out how much relic density is left over today. In particular, if this is a long-lived field, then that means that it could be dark matter. Now, recall that because this field went through some slow roll attractor, then the energy density that it's left with at the end of inflation was sort of independent of the initial conditions of the scalar. If the scalar started only a little bit far up or very far up, it would have reached the same part of the potential by the end of inflation either way. So this means that the relic density at the end of the day is also going to be independent of the initial conditions of the scalar. So this means the results from this part of the talk are going to be robust in that sense, and I'll come back to why that's important in a second. It will, however, depend on various inflationary parameters, so the Hubble scale during inflation or like the duration of inflation. These will be important for the relic density. So how do I track the relic density through radiation domination to today? Well, it'll undergo various phases, various equations of state as time goes on. So let's just go through quickly what that would look like. So it's got to end inflation the same way, it's got to start radiation domination the same way it ended inflation, which was frozen. So its energy density should be constant initially following the beginning of radiation domination. And then finally, it should, if I want it to be dark matter, then it should behave like matter today. So it should go like e to the -3 today. what happens in between, in principle, depends on the particular potential that I choose. So from this point, I now have to pick some particular potential. For the rest of the talk, I'm going to focus on a potential that looks like this, some quartic potential with a mass, because again, at the end of the day, I want it to look like dark matter. And so what will end up happening is that there's some intermediate regime where it goes like e⁻⁴. It behaves like radiation, and that's basically just the regime where the quartic term dominates. When the quartic term dominates, it goes like radiation. When the mass term dominates, it goes like matter. Good. So I can do this exercise of tracking through how much dark matter I get at the end of the day, and then I can say if I fix that to be the correct amount of dark matter, this will give me some relationship between the parameters of my potential. In this case, it'll give me some relationship between the quartic coupling lambda and the mass of my dark matter. Again, this allows me to draw some line in parameter space, which tells me dark matter lives here, and this is a nice benchmark for experimental purposes. And so here I want to just go on a quick aside just to compare to other sort of benchmarks in the literature, right? So for axion dark matter, we have a similar sort of misalignment band where we say in this band here, we know that we can produce the right amount of dark matter. Or for instance, for sub-GeV dark matter, we have this freeze-in line here that tells me that dark matter lives there. And these again are important benchmarks in the field. So for instance, this is actually coming from this Dominic M paper that was able to hit this freeze-in line, and that was a big deal because they hit this line that they were aiming for. And now, one of the reasons why people really take these lines seriously and really believe in them is because they're, to some extent, robust. There's some sense in which they don't depend too much on initial conditions. So the axion misalignment band, this is based on having sort of like an order 1 misalignment angle, right? As long as you have roughly an order 1 angle, you'll get this same amount of dark matter. Similarly, in the freeze-in case, this line is sort of insensitive to the initial reheat temperature of the universe, as long as this is like an IR freeze-in mechanism.
Further out, it's also constrained by the
Yes, yeah, that is true, and that is also a nice achievement that they. But anyways, the sort of long story short, the reason I bring this up is just to try to emphasize the fact that the reason that we take these benchmarks seriously is because of their robustness, because they're in some sense insensitive to initial conditions. And I want to argue that the line I'm about to show you is also the same. As I've argued, it doesn't depend on the initial conditions of the field, and therefore, in that sense, it's also a somewhat robust benchmark. So now I'll show you what this same type of line looks like in the case of quartic dark matter with some quartic coupling. Before I get there, I will preempt a very likely criticism, which is that the parameter space I'm going to show you is very technically unnatural. So the mass term that you would get from radiative corrections in principle can be very large. So take this.
Problem for any scalar.
Yeah, which is a problem for lots of both dark matter models and also inflation models as well. So this is not a unique problem to the potential I'm going to show you, but I just figured I would preempt that criticism. Okay, so this is the plot that I've been telling you I would show you. So here is the mass of the dark matter on this horizontal axis and the quartic coupling on this vertical axis. So this blue line here is showing you the line where I get the exact right amount of this dark matter to get the right amount of abundance. In colored regions here, I'm showing you various constraints on the model itself. So this red region here is where I produce too many isocurvature perturbations. So basically those power spectra I was showing you a few slides ago, this is the region where those lines would touch the CMB constraints. This yellow region here is where I would have too much of this scalar sitting around during BBN. It would mess up BBN, and effective during BBN would be too large. And then this pink constraint here is where the initial value would have to be larger than Planck. So if that's something you don't like, then don't go into this pink region. In these gray regions, I'm showing late time constraints on quartic dark matter. So this is coming from self-interactions or from structure formation. And then finally, in the dashed lines here, I'm just showing how these different curves all depend on one of these inflationary parameters, the Hubble scale. So as I change Hubble, these lines will move.
What do you call the mass?
What do I call the mass? What do you mean?
Yeah. Oh, it's a quartic by definition.
No, you had m squared phi squared plus lambda phi over 4.
Oh, there is.
Yeah.
mass.
Yeah. This,
Sorry, there is.
yeah.
I thought
No, yeah. For this part, there is now a mass term. Yeah. The mass term wasn't so important in the everything that happened in inflation. It's only later on that you actually care about it.
Is the tilt close to p equals 4 or close to p equals 2?
This is the p equals 4 case. Yeah. So this is you should think of this as the p. Yeah. This is the p equals 4 case.
And what is, so now you have something more specific, your initial value for the field?
So I know here the initial value of the field would be m Planck. Here it's going to be less than m Planck. In terms of what exactly it is off the top of my head, I do not recall. But I think I like basically set it to be yeah, so actually we could even figure this out. So I think I started it basically saturating this condition maybe slightly larger. So this is like lambda phi squared. This is h squared. So it's going to be like h like root lambda, h over root lambda times some order 1 factor. That's going to be over. Yeah. So in this plot, for the solid lines, h is 10 to the 12 GeV. If I pick here, let's say that's well, let's go down here, 10 to the minus 14. So that's 10 to the minus. So it would be, yeah, okay, I guess this is like 10 to the 19 GeV. There's probably some order 1 factors, but I guess it's close to m Planck. Like here it would be m Planck, but here it's probably like an order of magnitude or 2 smaller than m.
Yeah, the stochastic one would be h over lambda to the 1/4.
That sounds right. Yeah.
Which is much smaller.
Yes. Yeah.
And your energy density is lambda. So in the case you're starting up, if it's order m Planck, then your energy density is 10 to the minus 13 times m Planck to the 4th. And which is smaller than, a little bit smaller than the inflationary one.
Yes. Yeah.
Which would be about 10 to the minus 10.
Yeah. But again, if you go up to like this part of the curve, then you're probably more than small. Yeah. So there's definitely parameter space where you don't have to worry about the spectator being, or where the spectator is subduct. Okay. Nice. So the last thing I wanted to discuss was what happens to these perturbations during radiation domination. So I explained to you in the first part how the perturbations develop during inflation and where I get the tilt from. But in principle, they also evolve during radiation domination. I want to explain how that works. This argument can be basically understood in terms of the so-called separate universes approach. So what does that mean? That means what I showed you over the last few slides is how the scalar field, how the average energy density of this scalar field over the whole universe evolves. So I showed you that the final energy density will depend on the amount of energy I had at the end of inflation, as well as other parameters like, say, the Hubble scale during inflation. Now, if I think about 2 different patches of the universe, which are sufficiently large, then in particular much larger than the Hubble horizon itself, then each of those patches basically doesn't know about the existence of the other patch. Each of those patches thinks that it itself is the whole universe. So in particular, each of those patches undergoes exactly the same dynamics that I showed you before. It will just start off with different initial values for the energy density at the end of inflation. and the Hubble scale. What I really mean by the Hubble scale here is actually the local gravitational potential. If there's a little bit more gravity in one part of the universe, then it'll act as if there's a slightly different Hubble compared to the other part of the universe. But this relationship here between the final energy density and these initial parameters is precisely the same relationship that I calculated for the whole universe. So that tells me that the fluctuations at the end of inflation are going to be it can be easily related to the fluctuations in these initial conditions. The fluctuations today can be related to the fluctuations in these initial conditions at the end of inflation. In particular, there's actually a pretty nice way to read out what are the adiabatic fluctuations and what are the isocurvature fluctuations today. And that just comes from the fact, it comes from the dependence on these two different parameters. So any fluctuations in the energy density at the end of inflation, those are fluctuations which only affect the dark matter density today. They don't affect the standard model particle density today. And therefore, those are isocurvature fluctuations. They only affect dark matter. They don't affect other things. Whereas fluctuations in the local Hubble scale, which again is really the gravitational potential, those are fluctuations which affect all different components, and therefore they are adiabatic fluctuations. So again, these coefficients here, or these exponents here, will tell me precisely how the isocurvature perturbations and the adiabatic perturbations behave. This is precisely the same thing, just in some words with actual numbers now. So again, the separate universes argument, I'm just going to treat each patch, say each patch undergoes the same dynamics as the zero mode. So I can take the formula for how my final energy density depends on my initial parameters. This is if I had done the whole exercise of following the scalar field through the different phases of evolution, this is the answer that I would have gotten. I can take this expression and I can immediately read off how the final fluctuations will depend on the fluctuations at the beginning of inflation and the local gravitational, fluctuations at the end of inflation and the local gravitational potentials. And again, this first term is really telling me about the isocurvature fluctuations. This second term is the adiabatic fluctuations. And this term for the adiabatic fluctuations is the standard expression that you would get for any model. Importantly, this separate universes argument only applies for sufficiently large scales. So this basically applies for scales which are outside the horizon for the entire time that this thing is not acting like dark matter. So only scales which enter after this field has begin to already act like dark matter, and so standard cosmological perturbation theory would work for it. It turns out that scale is roughly this size for this particular dark matter mass. This exactly where this cutoff is will depend on the particular dark matter mass that I'm thinking about. So when I showed you this plot many slides ago, I had this dashed line here that I told you I would come back to. This dashed line is precisely telling you where the separate universes argument applies for this particular choice of mass. So these curves I was showing you here have this factor of 3/8 baked into them, but really you should only trust them to the left here if your dark matter has mass 10 eV. If you change your dark matter mass, then this line will be one way or the other. But long story short, the tilt of the potential is unaffected by any of this. Okay, so just to conclude, I've shown in this talk that I've introduced a new generic mechanism for producing blue-tilted isocurvature that basically just relies on two assumptions. One is that inflation is not too long, and the other is that the scalar has some non-trivial potential. Importantly, this mechanism really works for a wide class of potentials, and so I tried to argue that it's a somewhat generic expectation. And so you might actually, blue-tilted isocurvature is really something you should almost sort of expect for scalar dark matter. The reason this worked was because the scalar field spent most of inflation near the boundary of the slow roll regime, which is where the slow roll condition is marginally satisfied. And that slow roll condition was precisely that the effective mass was comparable to Hubble. And effective mass being comparable to Hubble is the thing that gives me a This is interesting because having enhanced isocurvature on small scales could lead to interesting signatures like gravitational waves and non-Gaussianities. And then finally, in the last part of the talk, I showed you guys that if this scalar is long-lived, then it can actually be dark matter. And in particular, the relic abundance is predictable. So the parameter space predictions that you get are actually robust to initial conditions of the field. So I guess the final thing that I want to leave you guys with is that dark matter could be as simple as just a scalar field with some quartic potential. And if it is, then what I've shown you today is a viable dark matter production mechanism with a robust benchmark. One of the best ways to look for it really might be by looking for small scale isocurvature. So thank you. I'll take it in.
Questions? Other questions?
In the late universe, when we accumulate a lot of dark matter in a small region, could it ever go to the regime where 5 to the 4 becomes important, or it's still dominant by?
That's an interesting question. I suspect it would have to be, you'd have to get it really compact because, so it has to be behaving like matter by, I guess not by BBN, by matter radiation equality. But that's still a Z of like 3000. So that's where I guess that's where the density is 3000. Well, it's like 3000 cubed times the average density today. So that's that's like a density of like 10 to the 9 times the average density of the universe. So you would have to get to even more than that before you could even think about, yeah.
No questions? Yeah. So if scalar is long-lived, the relic abundance is predictable depending on your, inflationary parameters. Can I ask how natural those parameters choice are to give you the correct relic abundance, or it's just a choice? N equals 60 to 80.
Yeah, to some extent, I would say it's sort of just a choice. So
there's no miracle like things that can happen.
yeah, so
initial condition.
the largest that Hubble can be is 10 to the 14 GeV. 10 to the 14 GeV won't work. That's already in the ruled out regime. So in that sense, maybe that was your most natural choice, but in principle, I think there's no issues with Hubble being smaller than that. So I would say that the Hubble scale is a relatively free parameter. The number of E-folds of inflation, again, I would say can kind of be anything. It has to be at least 60. 61 seems a little bit contrived to me, but as far as I see, there's no reason it couldn't be like 80 or 100. I should say, so again, there are two results in this talk. One is the dark matter density, which is this plot. The other is the tilt. So for the tilt, it really is important that N is fairly close to 60. You don't want N to be too much larger than that. For this part, you can still run the same argument even if N is much larger than that. And again, it's still robust benchmark that's insensitive to the initial conditions of phi. So yeah, you could increase this to 1000, and this line will just move down. So for here, the N can kind of be whatever.
So the quartic term is negligible when late universe, when square root of lambda times the typical value of the field is less than the mass.
Yes. Yeah.
Okay. If the mass is 10 and is 2 eV, and I saturate the energy density in our galaxy with this field, what's the expectation out of phi? It's still pretty big though, right? Well, I'm trying to check whether phi times the square root of the lambda is
Yeah.
smaller than that. If it's larger, then it's maybe not consistent. Something like that, the quartics.
Well, I guess I should also say that these are late time constraints. So like in this regime, this is
Yeah.
where
Yeah.
it's
Right.
large enough that the scattering
Yeah, I understand.
is important.
But I'm just trying to see if it's self-consistent. So square root of
Yeah.
lambda is 10 minus 8, then something like that. And what's the field of phi? So we need to saturate
Yeah, I mean
1 GeV per cubic centimeter with 10 minus 2 EV fields, right? So 10 minus 2 squared times. Let's calculate phi first for 10 minus 2 EV.
yeah, sure. Okay, so we said it was this.
No, but
No,
the
sorry.
phi from the observation, right? So we have 1 GeV per cubic centimeter divided by 10 minus 2 EV, right? Squared. See what I mean? I like to
yeah.
take the typical energy density of dark matter here and
Uh-huh.
estimate phi. I know that phi is going to be larger than EVs, right? A lot larger. No? Like
Larger than EV, you're saying?
You just have to fix the units.
yes.
Yeah.
Let me do the calculation.
Yeah, sure. If you want to.
Oral exam.
So I'm just saying that phi sort of is the square root of 1 GeV per cubic centimeter cube, right? Divided by the mass of phi squared, right? That's that's okay. So 10 to the 9 EV times okay, then it's not so bad. Then it's 8 times 10 to the minus 15 EV cube. Okay, so you're fine. 10 to the minus 4 EV squared. Put here 10 minus 3. Right.
Got into minus 8.
So what's that?
I got into minus 8. I just feel bad.
Was it?
I got failed expectation 10 to minus 8.
No, well, this is more like order EV, right? 10 to 9 EV, 10 minus
10 minus 2, 10 minus 1.
10 minus 1, right? So and
And the
square root of lambda is still much smaller than 10 minus 2, so it's okay.
Yeah.
Positive 9 negative.
What's that?
Actually, positive 9
Oh.
negative. Okay, so we quiz everyone. Great. Okay.
Nice.
So if no more questions, let's thank Saarik. Welcome back. Saarik has office in the FTPI visiting office. Please feel free to drop by and chat more with him.
I'll just be here today, but I'll be here all of today. So feel free to
Also,
come back.
feel free to join for dinner. Just let Saarik know.
Yeah. I'm down to get dinner